This is section 14.1, Vector-Valued Functions. We spent most of chapter 13 basically becoming experts in vectors on our quest to learn about all the different objects we need in order to say the important things we need in calculus. Here's our list of objects in Calc 3, and vectors were the first one on the list. That was basically all of chapter 13. What we're hoping to do in chapter 14 is really get into these kinds of functions, vector-valued functions, which are these two additional ones. Let's just jump right in. So the objectives for section 14.1, we're going to try to graph 2D and 3D vector-valued functions. We're going to try to parameterize explicitly and implicitly defined functions, representing them as this new kind of thing, this vector-valued function. And then find parameterized space curves of intersection. So we'll have two surfaces, and we'll find how they intersect. The two surfaces will intersect in a curve, which we will write down as a vector-valued function. And then we'll analyze some common features of vector-valued functions. We'll try to find their domains, we'll try to find magnitudes of some of the outputs, and we'll try to tell if these are continuous. I'll get these objectives up on the top so we can keep them there and refer back to them. And then let's move forward. So something that you hopefully saw in a Calculus 2 class is something called parametric equations. If you didn't see it, that's okay. If you did, that's great. But what is a parametric equation? Well, a set of parametric equations takes a number as input. This t is the parameter. You can have different parameters. The parameter doesn't always have to be t, but in these examples, the parameter is t. It takes t as an input, and then hands you back a point. So you say, hey, parametric equations, t equals 3. And the parametric equations say back, okay, here's a point. The way we write those down is usually as multiple formulas. So this is x equals t, y equals t squared. This one is a set of parametric equations. X equals cosine t, y equals sine t. This is a set of parametric equations. X equals 2 minus t, y equals 3t. And this is a set of parametric equations that's missing some letters. Let's fill these in. So this is x equals 4 sine t, y equals 9 cosine t. A set of equations that have the input of a parameter, t, and their output is a point. That's a set of parametric equations. This example says, what plane curve do these sets of parametric equations graph? And the main thing that you can do to deal with some parametric equations is just plug in some numbers. The difference is, unlike with a normal function from like Calculus 1, where you would plug in x and it would give you y, instead you plug in t, and plugging in t tells you both x and y. Up here, plugging in a number and getting out two numbers is this kind of function. You plug in a real number and it hands you x and y. So we're looking at this kind of situation. So what do? You pick whatever t you want, like, I don't know, I'll pick 0. When I plug in 0 for t, I get x equals t and y equals t squared. And then when I plot this point, I plot x, y. Then I can pick any t I want. So like I'll pick t equals 1. When t equals 1, x is t and y is t squared. I end up with the point x equals 1, y equals 1. When t is 2, well, x is still t and y equals t squared. So I get the point 2, 4. Notice that the parameter t doesn't end up on my picture. You can pick whatever. I'll pick minus 3, x equals t, and y equals t squared. So I'll get minus 3, 9. For each different value of t, I would get a different point. And I think you can see where this is going. We're getting a parabola. Didn't connect the dots very well there, but hopefully you can see what's up. One extra piece of information you get on this parabola, because it was a set of parametric equations, is that these t's are actually in order. The lower values of t are over here on the left, and the higher values of t are over here on the right. So instead of putting these arrows on the ends, like I would with a function, Instead, we should denote the orientation of the set of parametric equations by saying, well, the low values of t are over here, and the higher values of t are over here. So as time passes, I go this way along the curve. If you do this for all these different sets of parametric equations, you'll get different shapes. If x is cosine t and y is sine t, well, that describes the unit circle. And the unit circle parametrized in this way goes around counterclockwise. If you didn't know that, if you didn't remember that x equals cosine t and y equals sine t made a unit circle, you could just plug in values of t. So you'd say like, oh, well, when t is 0, cosine 0 is 1, and sine 0 is 0, and that would give you a starting point over here at 1, 0. And then you could plug in whatever other t you wanted, like maybe pi over 2. When you plugged in t was pi over 2, you'd get that x is 0 and y is 1, and that would give you another point to plot. And you'd keep plotting points until you saw what was going on. Up here I have x is 2 minus t and y is 3t. I really recommend this fallback plan, especially at the beginning. You just plug in a value of t and see what happens. So here t equals 0. If t is 0, then x is 2. If t is 0, then y is 0. And that gives me a point. And you can plot as many points as you want until you know what shape you're getting. So when t is 1, x is 2 minus 1, so x is 1. And when t is 1, y is 3. Now, I've seen enough of these that I know that these are linear equations, and they're both linear equations, and so I'm going to get a line here. So I already know that I can just like connect these dots. Until you get comfortable with the patterns, you should just keep plugging in points until you feel confident that you know what's going to happen. So when t is 2, x is 0, and y is 6. When t is 3, x is minus 1, and y is 9. Then I can connect the dots. Well, I tried to connect the dots. But notice that putting arrows on the end here is not really the way we should be graphing a line when it is a set of parametric equations. When it's a set of parametric equations, the arrows should be used to denote which way the curve is oriented. As t was getting larger and larger, I was heading up and to the left. So it's better when graphing a set of parametric equations to use the arrows to say, oh yeah, as t grows, the point is heading this way. Over here, x is 4 sine t, y is 9 cosine t. You can tell because there's a sine and a cosine that there's going to be some kind of oscillation, and maybe this is some kind of circular object, but the 4 and the 9 tell you that things will be a little bit stretched out. If you don't know for sure what the shape is, you just plug in a value of t. So this is the main takeaway, is that when you have parametric equations, you should feel like it's okay to plug in whatever value you want for the parameter and see what happens. Just like when you had a function in Calc 1, you had like y equals f of x, you were allowed to plug in whatever x you wanted to see a picture of it. Well, here you can plug whatever value you want for t. So I plug in these t's into x. I get sine of 0, sine of pi over 2, sine of pi, sine of 3 pi over 2 is minus 1. And then y is 9 cosine t. Then when I plot the graph, I don't plot the t's, I just plot the x's and y's. So I've got 0, 9, 4, 0 is next, then 0, minus 9, and then minus 4, 0. So this shape is an ellipse. And also, we can tell from the order that these points appeared that this is an ellipse that's oriented in the clockwise direction. So, this is our review of parametric equations. As we move forward in this class, we won't want to think of we'll want to think of this kind of object as one object, not as two parametric equations. But we want to group this whole thing together as one object, this way of thinking that's up above my head. That somehow we put in a number and we get back two numbers. Where when we think of them as sets of parametric equations, it's like I put a number into the first equation, it gives me a number. I put a number into the second equation, it gives me a number. So we'll want to gradually kind of like move past that. Okay, onto the second page. So each of the parametrically defined plane curves that we did on the previous page could be defined as vector-valued functions. Instead of saying, well, here's an equation for x and here's an equation for y, we put the equation for x and the equation for y into the components of the vector. And then we can think of the whole thing as just one object. This r of t we'll think of as the output when you put in a value of t is a vector. So that's where we are up above my head. Okay. So although r of t gives outputs that are vectors, and so they're not really points, we can't really plot them. Instead, what we do is we draw the vectors starting at the origin, and we take the terminal points of each output vector to graph it. So when I said x equals t and y equals t squared on the previous page, you could write it like this: r of t equals t comma t squared. And we think of that as the same object, just with a different perspective. That this is one object. It's one function, a vector-valued function, that takes an input of a number and hands you back a vector. This one was the circle, the second one. The third one was a line that was kind of headed off to the upper left, and the fourth one was an ellipse that was going in clockwise direction. If you're looking in 3 dimensions, you could have an input of a parameter, like a time value, and you could get back an x, a y, and a z, all 3. Well, you could think of this as 3 parametric equations, like a set of parametric equations, or you can mash them all together into one object by putting the x in the x component, the y in the y component, and the z in the z component of the vector. When you do that, you think of the whole deal as a single vector-valued function. That's this kind of object, where you put in a number and you get out a point in space, 3 coordinates. Again, these are vectors, they're not really points, but when we plot this kind of function, we plot the terminal point of the vector. So if we did this one, if we tried to plot this, for each value of t, we would get an x, a y, and a z, and that would allow us to plot what's going on at each value of t. So let's see an example. Oh, it tells us, the notes tell us here, that this vector-valued function, it actually makes a straight line. You can start to notice, you'll start to notice patterns as we go, but if the functions in each component are all linear functions, then you'll end up with a line. Is that always true? Kind of. As long as you only have one input, t, and you have linear functions in all 3 components, you'll definitely get a line. Okay, let's see some that aren't lines. So the first one is we've got r of t. The bold r tells you, oh, we're looking at a vector-valued function, where you'll plug in a number and you'll get out a point in space. You'll get out 3 numbers. The first component is, of course, the x, the second component is the y, and the third component is the z. When you go to plot this, you should try to plot it by plugging in values of t, just like we did on the previous page when we had 2 parametric equations. Here, we're just going to plug in a value of t and get out all 3 x, y, and z. So I'll just make a table here. You can plug in whatever you want for t. I recommend 0. When I plug in 0 for t, I'll get x, y, z of 5, 0, 0. And kind of the key leap here of thinking of this as a vector-valued function instead of thinking of this as a set of parametric equations is that I'm not thinking of it as three separate equations. Instead, I've got, that's t, and the output is the vector r of t. The operations you do are the same, but we want to be able to think about these three equations in a vector as though this is one function. It's just, instead of the input being a number and the output being a number, instead the input is a number and the output is a vector. And this kind of, this like abstraction of what a function can do is going to be really valuable if you can keep doing that, which is why I keep pointing at these objects over my head. Anyway, that's the point. This is the vector we get out from our function at t equals 0. And to graph it, I'll go out to x is 5, y is 0, and z is 0. Okay, let's plug in another nice value of t. This is all trig functions, so I'm going to plug in pi over 2 for t. In the I component here, I get 0. In the j component, I get 5. And in the k component, I get pi over 2. Okay, pi over 2 is like about 1.5. So where do I end up? I end up at x is 0, y is 5, and I'm like up a little bit, like 1.5. I can tell from the x and y being cosine and sine that there's going to be some kind of like spinning motion, but it looks like the z value is also going up. So I'm going to make a circle, but it's kind of headed up. Let's see where we go next. Just plug in pi for t. Well, now I get 5 cosine pi, 5 sine pi, and pi. So I'm back here at x is minus 5, y is 0, but I'm up by 3. Remember this trick that if you want to go up by 3, you go over here and you go up by the same amount. So I can see now what's going to happen. What happens is I go in a circle as far as x and y are concerned, but z is just rising over time. This is called a helix. I think you can see what's supposed to be happening here. So this vector-valued function, note that I'm not thinking of it as three functions. This vector-valued function, when I graph it in space, I get a helix that's going around and it's going up. Let's try the second one. This is u of t. You can call the vector whatever you want. It doesn't have to be r. What will I do? Well, I'm going to plug in t into the x component, the y component, and the z component, but we're thinking of this as one function. So plug in 0 for t. I get x is 0, y is minus 3, and z is 0. And that's a point I can plot. Let's try again. Pick another value of t. Because I have sines and cosines, I'm picking like nice angles to plug in. In fact, here, since I have a 2t on the inside, it wouldn't even be that bad for me to plug in t equals pi over 4. Plugging in pi over 4 for t would give me another angle inside the trig functions that's easy to evaluate. So I'll plug in pi over 4 for t. Then I'll get 3 sine pi over 2. That's 3. Minus 3 cosine pi over 2, that's 0, and t, which is pi over 4. Okay, where is that? X is 3, y is 0, and z is pi over 4. So this time, well, the magnitudes of the trig functions are only 3, so that's different in one way. And there's a bunch of things all mixed up, right? Like one of them has a negative sign on the outside, and the sines and the cosines have switched. But it looks like so far this one is going around in the same direction. Let's try some more values of t to see if we've got it right. So when t is pi over 2, I get 3 sine pi. Nope. Minus 3 cosine pi, that's 3, and pi over 2. Okay, so x is 0, y is 3, and I go up by about 1.5. This arrow, though. So we're still swirling around in kind of the same direction, but it's not going up as... Is it going up just as fast? I think it is going up just as fast, because the z-coordinate is exactly the same. Let's see where we end up at pi. At pi we have 3 sine of 2 pi, minus 3 cosine of 2 pi, and pi. 0 minus 3 is back here again. So they're both spiraling around in the same direction, but we didn't get all the way around on the first one until we made it up to t equals 2 pi. So the first time that we made it all the way around the helix one time, we were already up between 6 and 7. Where this one, by the time we get around once, we're only up at height like 3. So this will be a tighter spiral if we draw the whole thing. Basically, we get more loops per unit height. So that's the second example. What's the key thing that you're supposed to be taking away? First, don't be afraid of this object. You just plug in whatever value of t you want. Second, don't try to stop yourself from thinking of this as here is the function for x, here is the function for y, and here is the function for z. Our objective is to try to think of these as vector-valued functions, that in fact the whole thing is the output of the function. Okay, on to the next page. So here's another example. This is another vector-valued function where the input is any real number and the output is a point in space. We've got x, y, and z. So this question asks, what would the vector-valued function sine t, cosine t, t over 4 from 0 to 2 pi look like? And how would it compare with the previous graphs? Well, x equals sine t and y equals cosine t make a circle in 2 dimensions in the xy plane. But this z equals t over 4 means that as we go around the circle, we also go up. So let's just see what happens. I just did the thing. The whole point is don't think of it as x, y, and z. Instead, think of it as, oh, there's an input, which is a number, and an output, which is a vector. You'll notice that I usually use the same values of t to input. That's just because I happened to have these trig functions again. Remember in example 2, the second part of example 2, I actually did pick different values of t because I had sine of 2t and cosine of 2t. So just pick your values of t based on what you're looking at. Okay, when I plug in my t's, my parameter, into here, I get sine 0, cosine 0, 0 over 4, sine pi over 2, cosine pi over 2, pi over 2 over 4. Okay, sine pi, cosine pi, pi over 4, sine 3 pi over 2, cosine 3 pi over 2, 3 pi over 2 over 4, and sine 2 pi, cosine 2 pi, 2 pi over 4. So let's call this x. I, and z. It's probably going to be best to just go out by 1 here, because all of my x's and y's are between 1 and minus 1. And the highest my z gets is about 1.5. So I start at x is 0, y is 1. Let's get a different color. End up at x is 1, y is 0, and I'm up by a tiny bit. Then x is 0, y is minus 1, and I'm up by a little bit more. So we're spiraling around. And we come back up to the top. We come back up to the top when, or to the same x and y that we started with, when z is pi over 2, which is about 1.5. So this is the first loop of a spiral. How does it compare with the previous two graphs? Well, the x's and y's only ever get out to 1, where on the previous graphs, sometimes the x's and y's got out to 3 or 5, so those were larger spirals. This is all encoded inside this vector-valued function. Let's take a look at example 4. Example 4 says, what would the vector-valued function r of t equals 3 sine t cosine t, 2 cosine squared t, sine t graph? Okay. When you look at this, this isn't the kind of thing that you're supposed to look at and just say, oh, I know exactly what that is. That's not really the goal here. The goal here is for you to look at this and think, oh, well, I don't know exactly what's going to happen, but like I can decipher it. I can figure it out by plugging in whatever value of t I want to. Yeah, let's try. These are all trig functions again, so I'm going to try my favorite values of t. If it turns out, after I do these values of t, if I still can't tell what's going on, then I'll plug in some more values of t. Possibly, once I see a pattern, maybe I'll be able to go back and do something algebraic to notice, oh, these are all related in some way. But whenever you're stuck with a vector-valued function and you're just like, I don't know what this is, what do I do? You can just fall back to plugging in values of t. So I'm going to plug in t equals 0. I get 0, 2 cosine squared of 0, and sine of 0. Then I'll plug in pi over 2. Cosine pi over 2 is 0, so this first slot is 0. In the second slot, I get cosine squared of pi over 2, that's also 0. And sine of pi over 2 is 1. And I'll just go through and plug all these in. So pi, I get 0, 2, sine pi is 0. When t is 3 pi over 2, I get 0, 0, minus 1. When t is 2 pi, I get 0, 2, 0. Now, one thing I should notice here is, well, all of my x's came out to 0. And if that happens, I should check to make sure, like, is this actually always 0? And the answer is no, that's not always 0. So my values of t really aren't catching the whole story here. Let's try pi over 4 just to like see what's going on, maybe. Sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is also root 2 over 2. Here's 2, so I end up with 3 halves. Here for the y-coordinate, I have 2 times cosine squared of pi over 4. Okay. So I'm going to have 2 root 2 root 2 over 2, 2. Okay, well I can cancel some 2's. Looks like I get 1. And sine pi over 4 is root 2 over 2. I'm not seeing any particular pattern here. Guess I'll try to graph these. There's no way I'm ever getting past 3 for the x's, and there's no way I'm ever getting past 2 for the y's. So I have some idea of what my window should be. I spend a lot of time here at 0, 2, 0. I seem to come back here a lot. And I've got 0, 0, 1 and 0, 0, minus 1. What order does this go in? So I need to go from 0 to 0. This is where I start at time 0. Next up is this point, t equals pi over 4. So that's x is 3/2, y is 1, and z is root 2 over 2. It's like up here. And then I'm headed for, at time pi over 2, I'm headed for 0, 0, 1. So I kind of come out of the picture. Oh, it's this way. Interesting. Come out of the picture and head back up and then head back onto the paper for this. Then I need to make it back to 0, 2, 0. Weird. Where am I going next? I'm going to 0, 0, minus 1? So I must make a little loop like this too. What a weird shape. So z is going up and down because z is sine t. I don't like this. The x shouldn't... Oh no, this makes sense, because y is cosine squared t, so the y's are always positive, so that's why I'm always over on that side, on the positive y side. And then the x's could be positive or negative, so they're also going back and forth. So I think the graph is this like 2 loops. I'm not super sure of this. Anytime you're not sure of what your function is doing, you can always just plug in more points. So like I got a point up here. This was the t equals pi over 4 point. My guess is that there's another point kind of down here that's off of the yz plane, but that there's another loop down here. To test that out, I'll pick a t value that's a little bit past pi. So like pi plus another pi over 4. So I'll try t is 5 pi over 4. When t is 5 pi over 4, oh dear. Okay, so I'm a little bit past pi in the third quadrant. So sine and cosine are both negative. So I'm going to get 3 over 2 again. Cosine squared t comes out the same. Always positive. But sine t here is negative. Okay, yeah. So I do end up with the same deal. I have like a loop up here, and then a loop down here, and then it repeats. This is kind of awesome. So this is what a possible vector-valued function could look like. Now, what are you supposed to take away from this? What you're supposed to take away from this is the feeling of remembering what it was like when you didn't know a ton of different graphs of different functions. When you didn't know what like all the different functions looked like back when you were first doing algebra and geometry, whenever you got a new looking function, you would just grab it and be like, whatever, I'll just plug in a million x's until I see the pattern. And the point is to kind of like be humble and just look at this thing and go, I don't know what this is. Like, this could be anything. And just start plugging in points again. Except because it's a vector valued function, you're going to plug in values of t, and the outputs are going to be vectors, which you'll then plot in space. Or if there's only two components to the vector, you'll plot them in the plane. So the process here, and like not even the process, like the frame of mind is really what I was trying to communicate here. Okay, we've got a couple more concepts to look at. One is the domain. The domain of a vector-valued function is the intersection of all the domains of each component function. This means that for a number to be a valid input to a vector-valued function, it has to be valid in every single one of the components. As long as there's a value of t that is outside the domain of any component function, we say, yeah, okay, no, we're not plugging that t in to the vector-valued function either. So here, the domain of just the function 3 over t I can put almost any real number in for t, but I can't put in t equals 0. So this is all the real numbers except 0. Then I'll look at the next component function. The square root of t plus 2. Well, I generally am not very interested in taking the square roots of negative numbers when I'm thinking about domains. So I want to say that t plus 2 has to be at least 0. And that tells me what t is. T has to be at least negative 2. Finally, let's look at the last piece. I'm not sure about this yellow. Oh, we may never use this yellow again. Okay. The domain of this function, t squared plus 9t, nothing really goes wrong. I can plug in any real number into t squared plus 9t and everything goes fine. So then what do this is r, this is the real numbers. All reals. So what's the conclusion? The conclusion is I want the intersection, the overlap of all three of these domains. Where do all three of these domains overlap? Their intersection is, well, I can't go below -2. So I'll start at -2. And then as far as the second component is concerned, you can go up as high as you want. And as far as the third component is concerned, you can go up as high as you want. But the first component says, hang on, no zeros, please. Then as long as you skip over 0, you can do whatever you want. So the intersection of these domains is the domain of the vector-valued function. Let me see if I can, show you why we're using the word intersection here with a little bit better of a picture. I think I'm drawing under myself right now, so I actually have to scooch over. Okay, so the domain of the first component was everything except 0. The domain of the second component was, well, start at -2, but then whatever you like. And the domain of the third component was, sure, all real numbers. Plug in whatever, no big deal. If you took all three of these domains, the pictures of these domains, and kind of laid them on top of each other to see what the overlap was, like which points are shaded in all three cases. I wonder if I can just do that. Oh, I can't. Can I? No. The places where they overlap are the numbers starting at -2, going up to infinity, but skipping 0. So you can see it on the picture if you draw the 3 pictures and try to overlap them. Let me get my brush back. Okay, on to the 4th page. So what do we do with vector-valued functions besides graphing them? You can evaluate a vector-valued function. You do that by substituting in a value for t. Example 6. Evaluate the above r of t at t equals 3. Oh, I guess the one from the previous page. So this was 3 over t root t plus 2 and t squared plus 9t. No more yellow. Three over t root t plus 2 and t squared plus 9t. Evaluate r of t at t equals 3. Well, you write it by plugging in t equals 3 into every t. It's much easier if you don't try to overcomplicate the world very much. You say, oh, well, these things are equal for every t, so I just drop the correct value of t into all the t's on both sides of the equation. And that tells you the correct notation, which is that r of 3 is 3 over 3, square root of 3 plus 2, and 3 squared plus 9 times 3. So r of 3 is the vector 1 square root of 5, 36. We're not scrolling anymore. Okay, what else can we do besides graphing and plugging in points? Well, we can find the magnitude. Now, we found the magnitude of a vector a lot. So what is the magnitude of a vector-valued function? Well, the magnitude of a vector-valued function just finds the magnitude of each output vector based on what you put in. So you would write it like this. The magnitude of r of t is the magnitude of r of t. And since I'm trying to find the magnitude of r of t, I'll drop r of t in between these magnitude bars. Then you can find the magnitude of this vector. And it's a little strange because we don't know what t is, but that's okay. We know how to find the magnitude of a vector. Square each component. Add them together, and take the square root. It's possible that this simplifies in some way. If it simplified in some way, we would need the inside to be a perfect square. So let's just see if it is. Let's see if it's 3t squared plus 6 squared. Because then 3t squared squared would be 9t to the 4th, and 6 squared would be 36. If the middle term matches, then we can simplify this a lot. But here the middle term is going to be 2 times 3t squared times 6. So this isn't what we want. So never mind. So the magnitude of r of t is, well, there's not much to do here. We just found the magnitude. Now, the question is, wait, what happened here? We had a vector-valued function where you were plugging in a number and getting back a vector. But now, this thing, the magnitude of r of t, you plug in a number and you get out a number. So that's not a Calc 3 object anymore. This is a regular old function like you've done for all the rest of calculus, where you plug in a real number and you get out a real number. Okay, what else do we got? We've got some limits. If anybody ever wants the limit of a vector-valued function, you do the limit of each component. So if someone wants to know what's the limit as t approaches 2 of r of t, well, you go into all three components and apply the limit as r approaches 2 in all three components. Did I write r approaches 2? We're going to want t to approach 2, not r. r approaching 2 doesn't even make any sense. So I go into each component, and I'll let t approach 2. Now, how much do we remember about how to find limits? The easiest way to find a limit is if your function is continuous at the target of the limit, then you can just plug in the number. So here, since this function t squared minus 1 is continuous at t equals 2, the limit as t approaches 2 is found by plugging in 2. Here, this function is also continuous everywhere, so when I plug in 2, that's the value of the limit. The problem is this middle one. This function is not continuous at t equals 2. When I plug in t equals 2, I get 0 in the denominator. So I'll need to do some algebra before I can plug in t equals 2. Luckily, all this is set up to factor really nicely. So the numerator has a common factor of 2, and the denominator is the difference of squares. Inside the limit, I can cancel these two factors of t minus 2, and now the resulting function is continuous at t equals 2. So now I can plug in t equals 2. I get 2 over 2 plus 2. It's cosine of 2 pi, 1. So my final answer here is 3, 1/2, 1. So we handle limits the same way we handled them in older calculus classes. You just plug the number in if you can, and if you can't, you do some manipulations that will allow you to plug the number into the result. On to the last page. The last thing we're interested in is continuity. A vector-valued function is continuous on the intersection of sets for which its component functions are continuous. What? Okay, well this is the same definition as the domain definition. If you want to know where is a vector-valued function continuous, or where is a vector-valued function defined, you dig into its components, and you take the intersection of all the places that the components have that characteristic. So when we were finding the domain of a function, we just looked at the domains of all three components and intersected them. Here we'll do the same thing. So let's go back to that vector-valued function. The x component is continuous everywhere, and the z component is continuous everywhere. So the x component is continuous everywhere. The z component is continuous everywhere. And then all we have to worry about is where is the y component continuous? Well, the y component is continuous everywhere except where its denominator is 0. So everywhere except t equals 2 and t equals minus 2. If you look at the overlap of all three of these sets, the overlap is, well, everywhere except minus 2 and 2. So it's continuous from minus infinity up to minus 2, and then between minus 2 and 2, and then from 2 up to infinity. If you're taking a class that has access to Maple, you'll want to look at this and try typing in this code. I'm not going to put these things in every video because not every class will have access to Maple. So I think I'll end the video there. The next video is section 14.2. Let's look back at the objectives and see what we were dealing with. As far as the overall course objectives for like the whole class, we introduced vector-valued functions, which take a number as an input and output either a point in the plane or a point in space. For the section objectives, we graphed a whole bunch of different vector-valued functions. Sometimes they were spirals, sometimes weird like double loop things. And that was the primary thing that we focused on. Parametrize explicitly and implicitly defined functions. This was where we were trying to tell the difference between sets of parametric equations and a vector-valued function. And the answer is that it's mostly a matter of your perspective. When you look at a vector-valued function, like this one, sine t, cosine t, do you see this as 3 parametric equations where the parameter is a t, or do you see this as one function whose output is a vector? As you go through this chapter, you're supposed to more and more accept that this r of t is one object and not 3 objects. For the curves of intersection of two surfaces, we'll only do that if you have Maple. And then analyzing features of vector-valued functions. For the domain and continuity, that had to do with the overlap of the domain and places of continuity of the 3 component functions. For the magnitude, we just took the magnitude of the resulting vector and ended up with an old-style function. So that's 14.1.